Okay, so as mentioned, my talk is called Sleuthing in Cython. It's about my journey in wrapping and debugging legacy C libraries in Python. So what I'm going to cover today, the motivation and background for this project, a brief overview of Cython, what wrapping a library in Cython looks like, and what are some of the Cython conventions that are different than Python. Debugging and gotchas will be a significant part of the presentation, and then finishing up with package building. So in terms of my motivation and my background, so I started my career as a structural engineer. I worked on a lot of large infrastructure and cultural projects as both a building and a bridge designer. And I worked on projects where commercial software fell short, and a lot of commercial software for the built environment is pretty bad. So I wrote software to fill in the gaps, often with Python. So I've been working with Python since 2015, and it's kind of the language I keep coming back to. So I made a switch a number of years ago to working on digital infrastructure. I currently work at a company called Ready.net as a geospatial software engineer, expanding broadband in the US. I'm working on mapping projects. But I still will sort of jump at the opportunity to work on open source software, and I really want to contribute to projects that make open source software more accessible to the built environment. So what does a structural engineer do on a day-to-day basis? It's usually split between design and analysis. So the bread and butter of structural engineering is finite element analysis, and this is the idea of determining forces and stresses and structures, basically determining how little material can we use without an element failing. So in order to conduct this kind of analysis, you need to discretize a surface or a solid into a series of triangles or quads. So these are examples of contour plots that basically say how close the material is to failure. And the essence of finite element analysis is basically solving a system of sparse matrix equations to produce these kinds of stresses at each point within the element. So, as I mentioned, structural engineering and the built environment don't have that much in the way of open source software, but there is this open source package in Python to aid in finite element analysis of surfaces, planar surfaces, and arbitrary cross sections. So it's called section properties. It's built and maintained by Robbie Van Leeuwen, and this particular implementation requires triangular meshing, so taking a surface and making it into a bunch of little triangles for the analytic engine. However, so the analysis part is built on this other open source software called Triangle. So Triangle is a 2D quality mesh generator. It's used by section properties under the hood. So it was originally published in 2003 by Jonathan Shuchuk, and it's actually academic code, but it's very well documented. It's written in C, and it's used in many geometry libraries across a bunch of different languages. There's a Rust implementation. There are other wrappers in other programming languages. And one of the critical pieces of this mesh generator is that it produces triangular meshes that do not have small angles, because small angles produce bad results for finite element analysis. So I was actually contacted by one of the open source maintainers of section properties, Connor Furster, who'd seen some of my other work in developing with Cython, because I'd previously presented on building a constraint library with Cython at a past PyCon, and he was wondering if I'd be able to write another Python wrapper for Triangle that would be easier to maintain and update, because there is an open source wrapper for Triangle that if you do pip install Triangle, that's what you'll get. But it's updated fairly infrequently, and there have been talks on GitHub about like maybe we should fork this just to be able to have more control. It also doesn't build against all architectures. So I think most developers have seen this example from XKCD. Triangle is used in over 600 projects on GitHub. But this was the situation that the section properties folks found themselves in. So what Connor asked me to do was to create a new wrapper that would work on Python 3.9 and above and build on all architectures, because that was not the case. And we also decided to make it object-oriented because we thought it'd be nice to hold onto the object and be able to have interactive mesh changes potentially in the future. So the first sort of choice with wrapping this library was to use Cython. And why did I choose Cython? So there are a couple of different wrappers and ways to get C or C++ speed execution with Python. But the other libraries, so we've got like Numba, CUDA, Boost, Swig, they're not really object-oriented. It's more about matrix operations, very similar in syntax to NumPy. Some of the perks of Cython, it's really becoming more mature as a superset of the language. It allows you to keep Pythonic syntax, and you can mix Python files with the sort of Cython files. I have familiarity with this. I did a pretty in-depth project with it a couple of years ago, and the wrapper has significantly improved. There aren't that many maintainers for the package, but there have been a lot of advances in the past year and a half. So what is Cython? I know there's another Cython talk at this conference, so I'm going to be brief. So it's an optimizing static compiler. It's a superset of Python of the Python language. It produces C files, and it also produces executables. So what does it look like to wrap an existing library in Cython? So in terms of the directory structure that I ended up with, my source directory contains a directory that has the original C code from Shuchuk. It has another directory that's the Cytriangle directory, and that's where I have the Cython files. And so Cython files will have different extensions. We've got a .pxd, and so these are the header files, and a .pyx, and that's where most of the main implementation is. So let's see. So what I ended up writing was really just for 5 files. The C files are automatically generated during the compilation process by Cython, but those should be committed to a repository if you're going to build a package with Cython. So in terms of what the original C code looked like versus what needed to be mapped into my library, so there's the C struct on the left side and the triangle PXD on the right side. So there are 14 attributes. So these are lists that contain coordinates or references to coordinate pairs because we're dealing with geometry. So for example, the triangle list attribute has 3 integers per triangle that basically reference the different points in the point list. The other constants that are part of the C struct are for bookkeeping, basically to be able to know where the values end in the contiguous memory. That's part of the C code. So one of the classes I needed to create was the triangle IO class. That's a Cython class that wraps the struct directly. So there were key methods that I needed to fill in. You'll recognize some of these as methods or types of methods from Python. You've got your standard init, and then you have class methods and setters. But you might not be familiar with CINIT or dealloc, and so those are specifically part of Cython. So CINIT gives you the option of really making sure that that code is run immediately, and then the deallocation or dealloc is basically you have to manage memory yourself. This is one of the sort of the guns of Cython. And then what those other methods look like. This is just basically bookkeeping for getting everything into the right memory structure. So you do need to deal with pointers and memory allocation, but a lot of this is just like, how am I going to get from a C struct, which is not accessible in Python, to be able to basically access that as an attribute or a method on a Python object. So in terms of looking at setting triangles or setting triangle attributes, you need to use NumPy methods to get a contiguous array. And then you need to set the memory allocation based on the size and the value type. And then you have to iterate over the Python object in order to put it in the Cython object. And then the last piece of this is that, so I have my C-struct that now is part of a Cython class. For Cytriangle to run, it actually needs 3 instances of that object. So 3 instances of triangle IO. One of them is the input object, one of them is the output object, and the output object is initially null. And then there's also this Voronoi out object, which is just if you enable a specific flag within triangle, it'll get filled in. So I actually could have overwritten the original object, but I think there's some value in being able to see like what the mesh was previously versus like the mesh that you generate, because this triangle itself does have methods for being able to overwrite. And the other aspect of this is that Cytriangle uses all 3 types of properties from Cython. So you have CDEFs, which are only accessible in Cython objects. You have CPDEFs, and those are both Cython and Python. And then you just have your standard, Python definition. So, so this was an example of a CPDEF. It really is just like defining the method. And then these are just my standard Python definitions. So in terms of where I ended up with this project, I thought I theoretically had everything I needed to produce the package. Overall, this was less than 1,000 lines of code. The triangle library is something like 15,000 lines of code. So I wrote a test suite with PyTest. And it had 15 tests. I thought I was covering all of the different attributes and kind of different ways that you could generate a mesh. But what happened was I got this fatal exception only on the Windows build. It never happened when I ran a pipeline for Ubuntu or for Mac. And it didn't always happen either, but it always seemed to happen with GitHub. So it wasn't clear which test triggered it. I tried changing the order of the tests. I tried removing the tests. It just was not obvious where the problem was. And this code isn't particularly helpful. So I was dealing with the fact that different architectures had different build flags that I didn't have any control over, and different compilers. Like every single system could have had multiple different compilers that I used, and I was like, if I do a combinatorial matrix of all the possibilities, this is going to drive me nuts. So I was like, how can I reduce the complexity of this problem? So I did discover that this specific code on Windows indicates memory corruption. And the best way to track this was to use a memory profiler. So I wanted to try this on Windows, just because that was where the flagged problem was. But in going through the different options that I had for memory profiling, address sanitizer, ASAN, did not work with the Windows version that I had installed because it's not supported in Windows 11. It's only supported in Windows 10. For Mac, I didn't want to deal with the potential headaches from like messing with the system integrity protection. I tried ClangCL, had a lot of problems with getting like the wrong target, getting the right, like trying to use the right compiler. It was really just too fiddly for me. And so ultimately I decided to use Valgrind and check it against Linux because that seemed like the most straightforward path. And I figured that if doing this with Linux didn't work, then I would at least know, or like if Linux didn't return any errors, then I would know, okay, this is very specifically a Windows problem, and my other builds are probably okay. I also went back and looked at GitHub and other projects because there have been a couple of people that have, like, there's the original implementation of this. There's also another one that someone just did for fun. And there are a couple of things that I discovered when I looked at those other projects. I had thought that I really needed to preserve the original code from Shewchuck. It turns out neither of those projects did that. They made a couple of changes. And what I discovered is that on Windows, there was an underlying issue with the data type sizes for compatibility. So long was not the same size as the pointer on 64-bit Windows, which meant that my only option was to edit the underlying code from Shewchuck or add a macro to make this work. So lesson I learned from this, it was probably okay to modify the original source code, seeing as that is what others had done. But I was still having problems, so I turned to Valgrind. I found a pretty recent blog post within the past couple of years for configuring Valgrind for Python with Ubuntu, just a couple of lines of code to both install it and then configure it. And what I found from Valgrind, this is what some of the output looked like. It's pretty helpful. It does identify within the created C code from Cython where the issues are, like which methods. And what I could see from this was I was getting invalid write errors, and I was also getting invalid read errors. And so what this turned out to be was that I had misallocated memory in one of my initial files, basically saying that set holes only had a single allocation for a coordinate when it needed to have two, because it needed to have an x and a y coordinate. And then finally, it built. I was able to consistently pass the GitHub CI pipeline. But then, I needed to get this to work in section properties. That was the whole point of this. It didn't run in section properties. It was failing tests in section properties, and the error that I was getting there was that memory was being freed twice. And I looked at section properties, and they had a few more involved examples for tests than I did. And so I went back, and I was like, okay, how can I be freeing memory twice? This seems like this should be pretty straightforward. I mean, this is one of the problems with Cython, is that you do need to manage your own memory and make sure that you deallocate all memory from all of the attributes you've created within any of your Cython classes or objects. But this is pretty straightforward. The Cython examples online in their tutorials is just like, check if it exists, if it's not null, and if it is not null, make sure you free it. And there was nothing in here that indicated that I was somehow doing this twice. So I went back to Valgrind, and I looked at the input again, or I looked at the output, and the issue was that, obviously this is in the deallocation step, and I could also see how much memory was attempting to be freed that had already been freed. So I had an idea of like what size I was looking at. It was 16 bytes, so that's probably like 2 coordinates. And then I discovered further errors in Valgrind that also indicated the original allocation location. So it was for 2 different settings, basically setting holes and setting regions. And what do those physically mean in a mesh? Basically, you can add segments or boundaries to your mesh, and then to indicate that it's a hole, you basically put a point within a closed boundary. So that's what the hole is, and then the set regions is like, if I want to have more control over what the mesh looks like, you can basically tag, again, like a point to say, mesh this region in a different way. So at this point, I went back and looked at my tests, because my original test suite, I knew that I had included holes, like testing holes and regions. But I noticed that the flags that were being passed to my tests versus the section property tests were not the same. And so there are a lot of different flags that are getting passed into the underlying library. So I went through the ones that were being used, and basically what I discovered from triangle.c, so the original Shoochuck library, is that there was this macro that was being entered when the P flag was enabled. And I wasn't using it previously because it was just controlling an output setting that I didn't really need. But section properties does need that polygon output, like that format. So that's why it was in that section. And what I discovered was that in Shoochuck's version, it referenced the same location in memory for the out as in, because the input object and the output object, it was just easier to keep that reference because it should be the same data from the input to the output. So again, I changed the underlying code to explicitly copy the output whole list and the output region list to its own struct. And then, yeah, I also added additional tests from the library to make changes. Yep. So the real takeaway from this was use all the available resources. So look at GitHub for other examples, especially with Cython, because there aren't as many sample projects. Don't trust the underlying library that it's going to be error-free. Reduce the potential sources of errors, so keep it simple, stupid. And then different architectures can have unexpected results, but I think what was really important from this was that it wasn't just a Windows error. Like, one of the problems was just a Windows error, but there were other issues that were persistent across all architectures, but only Windows flagged it. So coming to the end, in terms of configuration, so I used Poetry to build this package. I know that we're not really supposed to use setup tools anymore, so a little bit of trial and error about figuring out which configuration was required now for a Cython project in terms of the build backend and what the requirements were for the build system. And then in terms of what the build ext.py file looks like, it has a couple of macros copied over from the C library, and the extensions are in cytriangle.io and cytriangle, and then there's just a build method command. So I've been using GitHub Actions to test against all the different architectures, but that's also what I ended up using for publishing this on PyPy. So I've got a CI workflow and publish workflow. I added the versions I needed from Python, so again, 3.9 and above. All of the different operating systems that I wanted to build against. So Ubuntu, Mac Silicon, Windows, and Old Mac. And then, yeah, this is just a couple of steps for downloading artifacts, setting up Python, installing dependencies, and then publishing to PyPy using Twine. And so this is an active project on GitHub. It has replaced Triangle within section properties as one of its dependencies. And with that, so that's the conclusion of my presentation. And thanks to PyCon JP and the Python Software Foundation for letting me come give this talk.
Thank you so much for your presentation, Maryanne. If anyone has any question, please raise your hand.
Thank you for your presentation. You mentioned in the presentation that you changed the underlying Shoochuck library. Was there a reason why you didn't go back to the original author and ask them to reintegrate those changes? And if that library were under active development, would you still have made these changes, or would you have been wary of getting out of sync with the original development?
I don't know if he actually, so he's an active professor at Berkeley. I think he gets many emails. It didn't occur to me because I was just like, if I can fix this and if I have control of the code, it'll be fine. But yeah, it is interesting because I don't think that, it's not that it doesn't work. It's just that in this context, it doesn't work, 20 years later and using different operating systems, so, yeah.
Anyone has any other question? Okay, then. So thank you very much once again, Maryanne. So that's another big round of applause for Maryanne.